Okay, so thanks for having me. Today I'm going to talk about imitation learning as cause-effect reasoning, so echoing a few themes that just came up recently and earlier in the conference. Okay, so first I'll just say a little bit about what I mean by this. So what is imitation learning? A lot of you are probably familiar with the idea. This picture shows what's going on. A father performs some sequence of actions, like screwing in screws to assemble some furniture, and a child, by imitating their parent, can learn a new skill. So imitation learning can happen at a sensory motor level, where a child learns about gestures and the kinematics and dynamics of its own body and facial expressions, which is a very important part, but there's also an important cognitive level to imitation learning. So for example, the child has a different viewpoint on a different portion of the environment. Maybe there are different tools available, different embodiment. So mimicking the precise arm motions and low-level motor actions is not appropriate. So one way we can look at that is that what the child is really imitating are the intentions of the parent. It observes what the parent is doing, interprets that, and forms a hypothesis that, oh, this must be my parent's intentions, which are causing them to do what I see them do. So in that way, cause-effect reasoning can play a role in cognitive level imitation learning. So why do we care about that here? I guess, to use that phrase, I guess I'm preaching to the choir, but roboticists are very interested in imitation learning as a way to give another form of human-level intelligence to robots. And imitation learning is certainly a very small piece of AGI, but it is a pretty general way of learning all sorts of procedural knowledge. And we know robots are great on an assembly line in a highly controlled environment, doing the same precise thing over and over, but if anyone saw the DARPA challenge, you know that as soon as you introduce variability, robots can really crash and burn. And a big part of that are sensory motor problems, but cognitive level imitation learning can also help us. It'll be another tool to help our robots adapt to new situations in a natural way, like in the keynote talk. And also, we've talked about the safety risks a little bit of general intelligence, and imitation learning keeps a human in a loop, so it can mitigate some of those risks. Okay, so based on these considerations, we wanted to devise an imitation learning framework based on cause-effect reasoning, and we had a few platforms in place to help us get started. We had this program called SMILE, developed by my colleague Di-Wei Huang. It's open source, freely available. It's pictured down here. And it's a very convenient graphical virtual environment where a user can click and drag objects to demonstrate a skill. We also have the physical Baxter robot. It's an upper torso humanoid robot. And so since we're interested in cause-effect reasoning and the cognitive level aspects here, we didn't really focus on sensory motor processing. So SMILE helps us bypass human motion capture and things like that. And for Baxter, we just use kind of homegrown, sufficient sensory motor processing to conduct our experiments, but it's certainly not state-of-the-art. So SMILE, as long as you give it the XML files for the objects, it can be used for basically anything. And the methods I'll discuss next are also supposed to be general purpose, but just as a concrete example, we'll use this learning scenario where we fabricated this docking station for 3D printed hard drives. And they have different slots and toggle switches and LED lights. And the idea is that Baxter should learn how to maintain it. If a demonstrator shows a skill like discarding a red LED drive, but then Baxter sees a new situation where a different slot is occupied, a different LED is red, we'd like, even from one demonstration, for him to do cause-effect reasoning and be able to generalize when things change to a certain degree. So at a very high level, this is the basic idea. You start with the demonstration in SMILE. There's a learning phase where you do cause-effect reasoning and try to infer the intentions that could have caused what you see the demonstrator doing. Then when you're encountered with a new situation, the robot does an imitation phase where it plans potentially different actions that will accomplish the same intentions. and then last it executes that plan. Okay, so I didn't really say anything about how any of that would actually work, so I'll get to that really quickly. But just to keep it concrete, I thought I'd start with some example videos of the framework in action. Okay, hopefully this works. Okay, so there's just an example demo being recorded in Smile. The user can set up their GUI controls, use toggle buttons for which hand is being used, click and drag to move objects. There's this light blue bounding plane that makes it easy to position things precisely, but the user can rotate that at any angle to move things wherever they need to. So here, this might be like a discard the malfunctioning drive skill, but Smile will just record a sequence of machine-readable, we'll just text format steps that this object was grabbed here, it was released here, and that's really the only input into the system. It has to infer what the intentions might have been. Okay, so they should be wrapping up here. In the interest of time, I won't quite let it finish. So next we have these two and three steps, which are the meat of it, but just I'll show you quickly the video of execution of that. So here Baxter is imitating the skill, and we hope he is generalizing a little bit, so you might notice a different LED is red now. So he's not going to do the exact same arm motion to go to the slot in the demonstration. He can also generalize in the sense that maybe the user used one hand for everything in Smile, but because of the physical constraints of his embodiment, it's hard for him to use his left hand to insert all the way on the right side of his body, so he does this handoff that wasn't included in the demonstration. Here he's just making sure he has a very accurate estimate of where it's positioned relative to his gripper, so that he doesn't get stuck when he tries to insert it there. Okay, sorry, I let it play to the end, but I was delayed getting started. All right, so let me say a little bit more about how that stuff actually works internally. So the basic way we try to tackle this is to basically posit this causal network as background knowledge. To keep things concrete, here are examples of the different intentions that might be in there and how, which ones cause which. At the lowest level, you might have things like just opening or closing a gripper or positioning the end effector at a certain pose. A little bit higher, you might have like a pickup, which would cause a few of those in sequence at the lower level, or handing something off. Further up, you might have generic get object from point A to point B intention, which in the simplest case is just pick up, put down, but it could also have a handoff depending where it has to go. If a gripper is already holding something else, it might temporarily find a free spot to put it down. So it can be fairly general. And during the learning phase, all the system sees is a sequence at the lowest level, and it has to infer from this soup of different intentions and causal relations which sequence of higher level intentions could have actually caused what it saw. And then the other step, it has to go downwards. It just has the top level intentions, and it might have to find a completely different sequence at the lower level for the new situation. So for the learning phase, we extended an existing model in AI called parsimonious covering theory of abductive inference. And for the downward level, we used hierarchical task networks, which were mentioned very briefly yesterday. So just to show some results of using this. For phase 2, the main thing we measured was just how long inference took to go in that upwards direction. So in all cases, kind of in the minute range, we recorded a number of different skills, 2 demonstrations for each one. So definitely not amazing. We want to improve that, but at least it finished in a practical amount of time so we could continue the experiment. And then in phase 3, we just looked at overall success rate. So the positive result is that we found it was actually correctly planning every single time a sequence of grasps and releases that would accomplish the skill if they were executed correctly. Although because of our sort of limited sensory motor processing, it failed during execution a fair number of times, just dropping during a handoff or 5 minutes. So we want to improve that more also. I guess I'm actually Yeah, just a few concluding remarks. So this is really just intended as a proof of concept, one way you might implement that high-level arrow picture I showed. Certainly has its limitations. Certainly doesn't address everything in artificial general intelligence, but I hope it's just made it a little more plausible that cause-effect reasoning is a promising way to do imitation learning and be able to generalize from one demonstration to some extent. Some future research directions. Well, we need to speed up those algorithms and maybe let them work on a richer knowledge representation. Although more, you may have guessed, there is a lot of knowledge engineering that goes into this. An analogy I like to make is with parsing. Like we provide kind of the grammar, and the inference rule is parsing, as if you think of actions as a sentence that it observes and has to parse. So it is doing some reasoning on its own, but we definitely had to provide more background knowledge than we want to. And lastly, to improve that sensory motor level, actually there's a parallel effort in our research group to use very bio-inspired techniques there that we want to integrate with this. And also one of these grand challenges of doing cognitive processing, symbolic processing with neural networks, not necessarily deep networks per se, but something bio-inspired. And we think that'll give a more natural human-robot interaction. All right, if I had 5 minutes, I don't know if there's time for questions, but maybe I'll defer.
I think we should go on, because
Yeah.
we're already behind schedule.
Okay.
And we're going to take the questions at the end. So please give him a hand.